All right, hi everybody. Today we're going to work on some practice problem videos over chapter 4.3. So this is going to be primarily focused on Newton's second law. And I'll remind you that Newton's second law states that a net external force is going to be directly proportional to the acceleration on that particular net external force, and it's also going to be related to the mass of the object. Okay, and so in mathematical forms, we say that F net is equal to m times a. I will also remind you that the other formula that was introduced in this chapter is that weight is going to be a form of the net force on an object times gravity, or I'm sorry, related to the gravity that the object is feeling. Okay, so let's start with our first one. And I like to draw pictures just like we always have. My runner has a mass of 63 kilograms and an acceleration of 4.20 meters per second squared. The question is, what is the external force on him? And so for us, we're just going to assume that the net force is just going to be related to mass times acceleration. So we're just going to multiply the two. Give me a second. Sorry, my calculator wasn't ready. All right, so multiplying those two together, we get a force of 264.6 newtons. Okay. All right. The next one says, if the sprinter from the previous problem accelerates at that rate for 20 meters and then maintains whatever velocity he's at for the remainder of the 100-meter dash, what will be his time for the race? So we want to figure out, using, of course, kinematics, how long it will take for him to get to 20 meters. And then we want to figure out how long it'll take, or how long it'll take, for him to go for the remaining 80 meters. So we're going to split this into two motions, 20 meters, and then 80 meters, obviously not drawn to scale. And what we're going to do from here is we're going to figure out how long it takes him to go 20 meters, then whatever velocity he's at here is the velocity he's going to go for the remainder of the 80 meters. And if we know that velocity, we can figure out time by just using the fact that velocity equals distance over time. Okay. All right. So let's figure out the first part of the motion. So over 20 meters, we know that x minus x naught will be 20. We know A. So we want to find t. We know initial v is 0, and we want to find vx, 2. So there are two variables that we are wanting to solve for here. All right, so if we're making our table, remember, we're going to fill in our variables. In this case, we're not using projectile motion assumptions. We are just going to pretend like there's just straight up initial final. Okay, so if this is all true, we want to find a formula that'll allow us to do Vx, and we want to find a formula that'll let us do just t. And so I'm going to write some of our, some of our formulas. I think I'm going to end up using this one to solve for t. And yeah, it's not looking great. It's probably going to be a quadratic if I do it this way. What other formulas do we have at our disposal as far as the kinematics equations are concerned? Hold on a second. We've got this guy. That might be useful for us when we're trying to find the final velocity. We've also got this guy. So that could actually be useful for finding the final velocity too. In fact, I think I'm going to use this guy to solve for Vx first, because it doesn't matter which order I solve them in. I only need Vx for the second 80 meters either also, so I know I have to solve for both. I'm going to use this one first, and then I'm going to use this one second. Okay. So for us, that means we need to figure out what the square root of 2 times 4.2 times 20. I got that Vx equals 12.96 meters per second. Okay, so that was step 1. Step 2, I'm gonna do this to calculate t. I'm gonna get 12.96 equals 4.20t. Divide both sides by 4.20. So just because we're not in the kinematics chapter anymore doesn't mean we're not using kinematics anymore. So you want to keep those skills in the back of your mind, ready to access. So I got 3.09 seconds for the first part of the race. For the second part of the race, how long does it take him to go 80 meters if he's traveling at 12.96 meters per second? And for this one, we can just use this one, because the velocity will be constant in this particular case. And we can use it to solve for t. And now I know it's going to go 80 meters is the final. I'm going to say the initial is 0. You could also do 100 is equal to 20 plus the 12.96 times t. These are both identical. One of them just takes into account that you start at x naught equals 0 and you end at x equals 100, instead of that this is one part of the motion and this is the second part. It doesn't matter which one you choose. Either way, t will come out to be 80 divided by 12.96, so 6.17 seconds for the second part of the motion. Okay, so now I have total time. All I have to do is add the two together. So I've got 3.09 plus the 6.17, and that'll get me 9.26 seconds. Okay. All right. All right. Next one goes back to our FNet and MA concepts, and says a cleaner pusher pushes a 4.5 kilogram laundry cart. So first thing I see is M is 4.50 in such a way that the net external force, so F net, is 60 newtons. What is the acceleration? So I'm going to use our new formula, plug in what we know. And I get 13.33 meters per second squared. Okay, moving on. In this one, we have an 18.3 kilogram child a wagon that weighs 65 kilograms. Now, whether or not these are important, we'll find out here in a second. Being pulled by the sister. If the sister is pulling with a force, I'm going to call her F sis, of 75 newtons. Ooh, and the friction on the concrete is 7 newtons. Then the question is, what is A? So in order to do this, we're actually going to draw a diagram. We're going to draw our first free body diagram. So here's my wagon. Here's my person inside. And here is my sister who is pulling this particular wagon. Now, I will remind you that when it comes to free body diagrams, we want to assume that the system, which in this case is going to be the wagon and the child together, are going to be treated as a point. And so we're going to draw our free body diagram. We're going to start with a point in the middle. And then we're going to add all of the different forces we know are acting. First is weight. And we always know that a weight force is present if we're on a planet. Opposite of that, and we talked about this in the video you watched, is the normal force, because we assume they're pulling on solid ground that's flat. We weren't told anything else. The next thing is going to be the F of the sister, which we were told is 75 newtons. And then the last thing is going to be friction, and friction always points opposite of the motion that's being applied. Okay? All right, so for us, we want to know F net. And in this particular case, F net is going to be equal to the force the sister is pulling minus the friction of the concrete. For us, that means 75 minus 7. So 68 newtons. Okay. So that's the first thing that we needed to know, is what is the net force on the system. Because the next thing we want to know is what exactly is the acceleration. And we know that F net equals mass times acceleration. So now we have F net. And can we figure out what the mass of the system is? Sure. We're just going to add the two weights together. And we're going to get 83.3 kilograms. Then we're going to plug in what we know to the equation to solve for A. And so rearranging the equation, you should do F net over M will equal A, which in this case will be 68 over 83.3. So in the end, we're going to get an acceleration of 0.816 meters per second squared. Okay, so that is just some brief how to do net force problems with also like a tossed in little review of our kinematics formulas, which took us a little bit. Yeah, so don't forget that these kinematics formulas, they still apply in situations. We may have to use them in various different random situations. Okay, so don't just put them on the back burner because we're not seeing them every day like we were before. All right, that is all for this particular video. The next thing you're going to work on are some practice problems kind of imitating the Newton's forces and the laws, okay?